let's talk about engineering stress and strain. The engineering stress and strain is a tensile test are defined relative to the original area and length of the test specimen. These values are of interest in design because the designer expects that the strains experienced by any component of the product will not significantly change its shape. The components are designed to withstand the anticipated stress encountered in service. The engineering stress is defined as the force divided by the original area. Here S is the engineering stress, F is the force, and A0 is the original area. The engineering strain is given by E equal L by L0. E is engineering strain, L is the length, and L0 is the original length. The stress-strain relationship has two regions, indicating two distinct forms of behavior, and they are: first one is elastic and second one is plastic. In the elastic region, the relationship between stress and strain is linear, and the material exhibits elastic behavior by returning to its original length when the load is released. The relationship is defined by Hooke's law, S equal capital E small e, where E, capital E, means modulus of elasticity, also known as Young's modulus, a measure of the inherent stiffness of a material. It is a constant of proportionality whose value is different for different materials. And there is a diagram of stress strain. Along the y-axis there is stress, and along the x-axis there is strain. And here 0.2% is absent. This region is elastic region. At the end point of elastic region there is y, and this region is plastic region. Here the maximum load is applied, and here the line is Ts, and the last line is fracture, from where the fracture started. As the stress increases, some point in the linear relationship is finally reached, at which the material begins to yield. This yield point y of the material can be identified in the figure by the change in slope at the end of the linear region. Because the start of yielding is usually difficult to see in a plot of test data, y is typically defined as the stress at which a strain offset of 0.2% from the straight line has occurred. More specifically, it is the point where the stress-strain curve for the material intersects a line that is parallel to the straight portion of the curve but offset from it by a strain of 0.2%. The yield point is a strength characteristic of the material and is therefore often referred to as the yield strength. Other names include yield stress and elastic limit. The yield point marks the transition to the plastic region and the start of plastic deformation of the material. The relationship between stress and strain is no longer guided by Hooke's law. As the load is increased beyond the yield point, elongation of the specimen proceeds, but at a much faster rate than before, causing the slope of the curve to change dramatically, as shown in figure. Elongation is accompanied by a uniform reduction in cross-sectional area, consistent with maintaining constant volume. Finally, the applied load F reaches a maximum value, and the engineering stress calculated at this point is the tensile strength or ultimate tensile strength of the material. It is denoted as Ts, where Ts equal maximum force by original area. Ts and Y are important strength properties in design calculations. Conventional tensile testing of ceramics is difficult, and an alternative test is used to measure the strength of these brittle materials. Polymers differ in their strength properties from metals and ceramics because of viscoelasticity. To the right of the tensile strength on the stress-strain curve, the load begins to decline, and the test specimen typically begins a process of localized elongation known as necking. Instead of continuing to strain uniformly throughout its length, straining becomes unconcentrated in one small section of the specimen. The area of that section narrows down, that is next, significantly until failure occurs. The stress calculated immediately before failure is known as the fracture stress. The amount of strain that the material can endure before failure is also a mechanical property of interest in many manufacturing processes. The common measure of this property is ductility, the ability of a material to plastically strain without fracture. The measure can be taken as either elongation or area reduction. Elongation is defined as L equal LF minus L naught. LF is the final length, L naught is the initial length, and this L naught also. Area reduction is defined as AR equal A naught minus AF by A naught. A naught is the area, initial area, and AF is the final area. And thank you for being with me.